Structures of ionic solids. Now let's talk about a few select ionic solids and some slightly more complicated structures. We're going to talk about what types of ions form what types of crystal structures. You'll need to know the crystal structures for cesium chloride, sodium chloride, zinc sulfide, and calcium fluoride, and for other ions that match the most likely structure if given the radii of the atoms. And this will make far more sense as we go through it. Let's start with structures that have a 1-to-1 ratio. The 1-to-1 ratio helps us decide between three different structures. Which of the three it forms is going to be based on the size of the ions. If the ions have a very similar size, it will form a body-centered structure as shown here. Note that these are not space-filling models as I showed in the last video, just for clarity so that you can see everything. Here I have a cesium chloride shown. Just to show that it's a 1-to-1 ratio, let's show how many atoms per unit cell there are of each and where this comes from. The cesium is completely within one cell, and so there is just one, and there is one of them. For chlorine, there's 8 Cl-, but they're on each corner. And so as we talked about last video, the ones on the corner only have 1/8 within this own cell because there's 1/8 in each of the 8 different cells surrounding it. So this gives us 1 cesium and 1 chloride. If there is a mild difference or a medium difference in size, there's another structure that it can form. And this is sort of like a simple cubic structure, but with alternating atoms on each corner. So the one I have here is sodium chloride. In order to get one pattern that repeats itself, it actually requires 8 cubes, as you might think of it here. So what I have shown here is not 8 cubic cells, it is 1 cubic cell, even though there happens to be 8 in them. Let's go ahead and count our atoms. For the sodium, there are 8 atoms on the corners, which have 1/8 inside the cell. There are 6 on the faces, so take a moment and find those. There are 6 on the faces. Each of those are half within the cell, and so they count as half. For the chlorine, there is 1 atom in the center, which belongs completely to that cell. And then look at where all the other chlorines are. They're all on the edges. So if they're on an edge, they are 1/4 within the cell that we have here. So if we compare all of this together, that gives us 4. So we have 4 sodiums and 4 chlorines, once again giving us a 1-to-1 ratio. Now let's look at another one. For the last one, this will happen if there is a big difference in size. It'll form what we call a zinc blende structure. This is sort of like a face-centered cell, but with 4 atoms in the alternating holes that would come from a face-centered. The zinc ions are all within the cell, so there are 4 of them. The sulfur atoms have 8 on corners, which contribute 1/8 each. And then there are 6 on the faces, which each contribute 1/2. So this, once again, gives us 4 of each atoms, or a 1-to-1 ratio of zinc and sulfur. Now what about if you have a 2-to-1 ratio or a 1-to-2 ratio? If it is a 2-to-1 ratio, it will often form a fluorite or antifluorite structure. These are basically the same, except that the fluorite structure has 1 cation to every 2 anions, whereas the antifluorite structure has 2 cations to every 1 anion. Let's look at the fluorite. Calcium fluoride crystallizes into this structure. It has 8 fluorine atoms that are completely within the cell. And then for the calcium ions, it has 8 corners with 1/8 each, and 6 on the faces accounting for 1/2. This gives us a total of 4. For antifluorite, like lithium sulfide, it is the same, except that the positive lithium is on the inside of the cell, and the negative sulfurs are on the corner in the faces. So these can be counted the same, with lithium being completely inside the cell accounting for 8, and sulfur 8 on the corners accounting for 1/8 each, and then 6 atoms on the faces accounting for 1/2 each, for a total, once again, of 4. Let's do an example now. Of course, I could always ask you to match these with the ones that I just gave you, and you should be able to do that. But I can also ask you about other ions, and based on their size and their ratios, you should be able to figure something out. Here I ask which is most likely of our options shown here to crystallize into a zinc blend structure. Now think about what I said about zinc blends. We know that the zinc blend structure has a 1-to-1 ratio with a big size difference. So here we're going to be able to rule out one of these right away because it has a 1-to-2 ratio. So right away we get to rule out our magnesium chloride. So now we need to look at our rubidium chloride and our copper iodide and see which one has the biggest difference in size. So take a moment and compare these together. When we look at these, we can see that one has a much greater difference in size. Where one is only a little over 1 as big, 1.25 times as big. The other is 2.25 times as big. So because of this, our copper iodide is most likely to form our zinc blend structure. And that has to do with the ratio and the comparative sizes. In review, we can now match cesium chloride, sodium chloride, zinc sulfide, and calcium fluoride to their unit cells. You need to know these structures. For any other structure, we can tell which of the structures we discussed is most likely based on their comparative sizes and their ratios.